Hello everyone, in this video we'll be reviewing chapter 4, which is where we started integrating. I am so sorry that you can see all these markings. I feel like it's bothering me, so I know it's probably bothering y'all since you have to watch this in video. I need to start writing lighter, but I don't think about it at the time. So try to pretend this is a nice pretty white piece of paper. So when we started integrating, we first talked about indefinite integrals. So that is when you integrate a function and there's no boundaries. So if I integrate f prime of x, and you always write dx, that just means that with respect to x, the variable in here should be x. Then that would just equal whatever the antiderivative is, right? So what's the antiderivative of f prime? The original f of x, and then you would have your plus c, right? And so then that is indefinite integral. When you do definite integral, you have the integral and you have boundaries a and b, and if it's still considered f prime in here, so you still take the antiderivative, which would be f of x, but then you do f of b minus f of a, which actually we're going to write down there, and it's going to be a number, right? This is an equation. I swear my dog knows when I film these videos. It's so weird. But yeah, so when we do an indefinite integral, you're just getting the antiderivative, the original function. When you do a definite integral, you're getting an amount, a number that accumulated over time. So indefinite integrals give you the general solution with the plus c. So if you plug in your initial condition, oh my gosh, hold on, initial condition, then you get the particular solution. Okay, so that ties into slope fields, which we'll review with chapter 12, but right, general solution is all the different shapes, and then particular solution is just one that goes through your slope field. So if you're trying to integrate, here are some strategies you can use, because really and we'll write this down, but the only real thing you can do for integration is use substitution, right? We don't have product, we don't have chain, so if you want to use something, first you can think about these algebra options. So the first option you have is before you take the antiderivative, you could expand it, which just means like FOIL or distribute. Right, so an example would be if you had the integral of 1 plus e to the x squared, and you didn't know what to do. Well, we could actually try to expand this before we take the integral. Because again, we don't have like a chain rule, and use substitution I don't think would even help you here. So what it would want you to do is to actually write it out, 1 plus e to the x times 1 plus e to the x, and FOIL this inside the integral. And that would become, when you FOIL 1 times 1 is 1, outer is e to the x, e to the x times 1 is e to the x. Now you have e to the x times e to the x, which is like e to the x squared, right? So then we could clean this up, and it'd be the integral of 1, e to the x plus e to the x is 2e to the x, and then when you have an exponent on an exponent, you multiply them. So that would be plus e to the 2x. And then now we could integrate each term, separate the integral. I don't have room to write this down, but the integral of 1 would be x. The integral of 2e to the x just stays 2e to the x. Here you would have to use u substitution, and you make u the 2x and do your du. But that's not what we're going to review right now. I was just trying to show you a strategy. Another strategy is you can separate the numerator if there's more than one term on top. So, for example, if you have the integral of, let's say, 1 plus x over x. So we don't have a quotient rule for integration, so we would need to try to do something else. So what I would suggest is you can, if it's one term on the bottom, or you got to keep that whole thing on the bottom together. So we could separate that and rewrite it as the integral of 1 over x plus x over x. And then we know we can keep this the integral of 1 over x plus, that's just 1. And then we could do this, the integral of 1 over x is natural log plus x, and I'm just going to leave them here. You can actually try to take the antiderivative, and if you want to send me a picture, I'll tell you if it's right or not. Now, we haven't done long division a lot, but I want to go ahead and show you all this. So let's say you had a problem like x squared over x squared plus 1. I will say you cannot try to divide up x squared over x squared plus x squared over 1. You can only divide it if it's more than one term on top. Okay? You cannot do that here. That would not be mathematically sound. But what you could do, if you have the same exponent or a bigger exponent on top, you could try long division to rearrange it. So the top goes inside, the bottom goes outside. So when you do long division, you divide the first terms. So what's x squared divided by x squared? 1, and then you multiply and you write it underneath. So that'd be just x squared plus 1, and then you subtract this whole thing from above it. So x squared minus x squared, I'm going to kind of go into here, is 0. And then this is already 0. So 0 minus 1 is negative 1. So we have a remainder of negative 1. So once you get to your remainder, this is kind of a short problem, but because this exponent is smaller than x squared, we know we're done. So what does that mean is you can rewrite x squared over x squared plus 1 as your answer, which was just 1. Then since our remainder is negative, we're going to put minus. If it was positive, I'd put plus. And you write your remainder over what you divided by, which was x squared plus 1. And now it's two different terms. So we can integrate 1, which is just x, and then here you would need u substitution, which now I'm thinking you would still have an x. So that would be a messy problem. I wouldn't try to go actually do this one. I just wanted to show you the strategy of long division. Another thing you could do, and we haven't done this one either really, but just real quick, and again, if this doesn't stick, you probably won't need it, but let's say I gave you that same problem and you don't know long division. I can't really give you a good strategy on how you would know to do this, but sometimes it helps if you add or subtract a term in the numerator to make it match down here. Right, so what I could do is let me write my dx before I forget. Because this is close and this is plus 1, so if I did plus 1 up here, but then to make sure I didn't change my problem, I'd have to also do minus 1, right? If I add 1 and subtract 1, that's 0, so I didn't really change my problem. But now I could rewrite this as, I'm going to write it all out. I know that looks like the same, but now I can separate the numerator if I keep my denominator all together. I cannot separate this x squared plus 1, but if I kind of treat that as one term, because I know those are the same, and then I divide this minus 1 by x squared plus 1, I'm allowed to do that. I didn't separate my x squared plus 1 on the bottom. And that would turn to x squared plus 1 over x squared plus 1 is just 1 minus 1 over x squared plus 1, and you can see that's the same as this, as doing long division. So those are some kind of more algebra-based methods that we haven't focused on. Just wanted to show them to you. And another thing you could do is use trig identities to help you, which I know we're not the biggest fans of. So an example of this could be if you had the integral of cotangent squared. So that is no one's original derivative, right? So we're saying whose derivative is cotangent squared? Well, if we look at these trig derivatives, cotangent squared isn't one. So we think, can we use a trig identity to get this to be something we know how to take the integral of? And again, I highly doubt this will come up, but just in case, if you know those basic ones, the integral of cosine and the integral of sine, you'll probably be fine. But so there's a lot of different identities you could do with cotangent squared. The Pythagorean identity that we have, if you go back and look at it, it's that I'm going to write it over here. Cotangent squared equals cosecant squared minus 1. It's a form of the Pythagorean identities. So I could rewrite my problem as cosecant squared minus 1, which, why is that better? Because whose derivative is cosecant squared? Well, that's really close to this. If it's just a negative difference, then I can just negate the answer. So it's like pulling out the negative. So whose derivative is cosecant squared? Well, negative cosecant squared is cotangent, so it's going to be negative cotangent. So I'll actually integrate this one. The integral of cosecant squared will end up being negative cotangent, because the derivative of negative cotangent would be cosecant squared. Remember, always check your work, think going backwards. And then the integral of minus 1, the antiderivative of minus 1 would be minus x. And then you put your plus c. So this is the only one I actually integrated. So now if you can't do algebra, the only other rule you have, only other option is u sub. Okay? So if you get stuck on an integral, you need to try u substitution, which you have notes over that. I'm not going to really go over the full u substitution, but that's where you pick your u, the inside, take your du, and then get it all in terms of u, integrate it, and then replace your stuff back. And so remember, if you're using u substitution, you need to either change the boundaries or on a definite integral, or you need to make sure you replace u with x before you plug them back in. So that's what I was writing here, and then I realized I was writing it on the wrong one. I meant to write this on my own copy. I hope y'all just hear my dog barking in the background, but I'm not letting him back in because he insisted on going outside. I lied. I'm gonna let him in. This is fine. Okay, so you either need to change the boundaries if it's going to stay in terms of u, or change back to x. I know it's probably hard to read because I have this mess that was already here, but change it back to x before you plug in the boundaries. So if you don't understand what that is talking about, it was your notes when you first came back after Christmas break for the semester, and there's u substitution notes, and at the very end we talked about the boundaries. Okay, so then ultimately what you need to understand is, what is the integral? A definite integral, it gives you the area under the curve of whatever you're integrating, right? So how do we find a definite integral? Maybe I'm going to write this on top. Ways to find a definite integral. You can either use a calculator, use fundamental theorem, FTC, that's what this is. You can find area using geometry. That's when you just use the shapes, right, of a triangle, of a trapezoid. And those are the three main options. Another option would be like they give you properties and you can piece it together, but I don't think I'm going to put that up there. Okay, so if we're going to do area, it would have to be geometry. Now sometimes when you can't actually solve it, if it's not a perfect triangle to find the area underneath, or a perfect trapezoid, then you estimate it using Riemann sum. So Riemann sum left, right, and midpoint are all rectangles. So what's the formula for area of a rectangle? It's base times height. So what is the base? It's the width. And so how do you know the width? If it tells you it's equal width, I'm going to say for equal width, the formula is you take b minus a divided by n, which is how many rectangles you want. And this is like the endpoints for the interval that you're finding the area underneath. So if you want 4 rectangles, then your n would be 4. And so that's going to get you the width for all of these. That doesn't change. Now the height is a y value. So how do you know what the y value is? It depends on what type of sum. If it's a left sum, you're going to use the y value from the left side. So you start at the left. And so what that would look like is, let's say you have this function, and we're going to draw a rectangle starting on the left side. And let's say we're going to do 4 rectangles. So you go up, over, down, all the way up to your function on the left side, over whatever the width is, down, up all the way to your function on the left side, over whatever the width is, down. So then if it was a right Riemann, you would do the exact same process, but you start on the right side. So your width is the same formula, but your y value is coming from the right side of the rectangle. So if it was the same picture, and I would start on the same here, but I would go over to the left, or sorry, to the right, and I'd start on so I'd start like on the b value instead of the a value. And I'd go straight over my width all the way down up to that where that y value hits. So you notice I'm using these y values. Over, down, over, down, over, down. So I use the y value for the right side of the rectangle. Here I use the y value on the left side of the rectangle. And then midpoint is you use the middle y value as your height. So what would that look like if you had the same looking function? Well, you'd find your width. So let's say the first rectangle goes from here to here. Well, then you'd find the middle and find that y value on your curve, and then you go over to the left side, over to the right side for that rectangle. Same thing if the next one goes from here to here, you find the middle, find that y value, and you go over to the left, over to the right. If you have one more, find the middle, go up to that y value, over to the left, over to the right. And normally these are tables, so sometimes drawing it makes it almost more confusing. On a table it'll be easier because you just use the left y value or the right y value or the middle y value. Or if it's trapezoid sum, you use the formula for a trapezoid, which is 1/2 height times base 1 plus base 2. But now in this case, your height is your width, and then your heights are like your bases, so it kind of switches. And these heights are going to be y values, the left y value and the right y value for the trapezoid. The width is the same formula that we used here. Okay, so the next stuff is more just like formulas. So we have our fundamental theorem, which we already set it up here. So you take the first, don't forget, some of y'all forget to take antiderivative before you do f of b minus f of a. That's why it's capitalized here. It's the same thing as thinking as the inside's prime, so then the outside one has to just be normal f. Take antiderivative. And then you do f of b minus f of a. And what does that give you? It gives you the total gain over a certain time. So like if you integrate, remember, gallons per hour, then this is the total gain of gallons. If you integrate miles per second, then this would give you total amount of miles because over this interval. Another word that's good to use is net change. It gives you the net change over the interval. Okay, so then it says, remember to find the total after a certain time. You have to use your initial condition. just said f of k, but I'm going to change that to be f of a. So it's using this, it comes from here, it's just manipulated this to move f of a over to the other side. But, so if you move f of a over to the other side, you would have f of b by itself equals f of a plus the integral from a to b of f. Now normally this is a derivative, so I'm going to put f prime, because normally that's a rate. If it's not a rate, then this wouldn't really work. And so this would give you the total amount at whatever time b. Right, this just gives you how much you accumulated over the interval, but to know how much you actually have, the total, you would have to add what you started with at the beginning of that interval. So you got to add your f of a. So that is where the formula comes from that we used a lot in those chapter 3 free responses. So if you want a formula for f of x, it's the same thing.